even if you have tons, like 20 and 30 and 40 electrons, their mass is so minute that it doesn't even really even, it's not significant enough to even add into the mass of that atom. Proton, though, we consider it to be 1, and the neutron is 1 to 1. They weigh about the same. Remember, Chadwick said that he was taking the mass, and the mass was like half, right? We only had one part. We were missing the other part, which was the neutron. Why were we missing it? Because it has no charge. No one was able to see it. And then the actual mass, believe it or not, and we're going to need this number. The actual mass here is 9.11 times 10 to the negative 31 power kilograms. The proton and the neutron, which pretty much weigh the same, which is 1.67 times 10 to the negative 27 kilograms, and 1.67 times 10 to the negative 27 kilograms. Okay? Let's keep going. It says here the whole. Let's talk about this atom as a whole. The inside the nucleus, though, we know is comprised of these protons as well as the neutrons, right? Overall, the atom has a positive charge. Inside the nucleus. I'm sorry, I said overall, but I meant to say in the nucleus. So the whole atom. Now we're breaking it up into the nucleus versus the outside. Why is it positive? Because neutrons have no charge. The next part here, it says, though, it's very dense. Now, we know that it's extremely small, but extremely small percent of the total volume of the atom, but it's 99.97% of it is of its mass. So the proton and the neutron combined together in the nucleus that's extremely compact, okay, comes up to be 99.97% of the mass. That's how little insignificant that the electron's mass is. Now the outside part, right, the outside, which we call those outside the nucleus, those electrons, 99.9% of the atom is roughly just empty space in which the electrons travel around in that empty space. Overall, it's going to have a negatively charge on the outside. But if I have a positive and negative, they cancel out, and my atom should have a neutral charge. But we'll talk about that later. Let's see, we talk about it right now. Let's see what it says. How they fit together. Electrons are held within the atom due to their attraction to the nucleus. So they are attracted to the nucleus. But here's the but, though. So why don't the electrons suck into the nucleus and then it collapses? Because the neutrons actually help stabilize those in the nucleus. They're like buffers, like a buffer zone. Okay, rather than that electron suck to that proton so quickly, those neutrons are in the way, buffering and saying, hey, hold up, you're not going to come inside here and just attach to the protons. They stand in the way. Okay, they act like a pillow, a buffer that separates them, right? Here's the problem, though. Too many neutrons can make the atom radioactive. Okay, and we call it unstable. All right, I'm sure you've heard about radioactive material. Why is it radioactive? Because there's too many neutrons and it's unstable. What does that mean? There's too many neutrons inside that nucleus of the atom that it's unable to hold everything. Imagine going to a buffet, right? And you have your plate. And it's a buffet, so you can fill up that plate as much as you want, but you are starving. So you fill up that plate as much as you can. Now, you can't get a second plate just yet. After you eat that first one, you can go back. But what do? You fill it up and you fill it up. And then this is a huge buffet. And you're not even through the end of the line yet. and you still see more things that you want to try this and you want to eat that, and you continue to add it to your plate. That's what's happening here with the radioactive atoms. And it might get to the point where you have a little bit too much, and some of it is what? Falling out. And when that occurs, that's when we have unstable radioactive atoms. Okay, they're falling out. There's too much to stay in there. Since all atoms are electrically neutral, this is a super important part. I'm going to definitely highlight this for us and like star it. Since all atoms are electrically neutral, it says here. Why? Because the positive protons equal the negative electrons. And so they cancel each other out. And so my atoms are originally all neutral. One more time. All atoms are considered to be originally neutral. Okay? Now let's keep going. And we're going to talk about what we call the Bohr model, right? So we talked about we're going to talk about his Bohr model. Now, the Bohr model is pretty awesome, but we like the Lewis dot structure better. Yeah, we like the Lewis dot structure better. But let's go ahead and keep going with this one here before we stop and go and take a break. Bohr model says that we've got positive protons and neutrons that are located in the nucleus. Yes, write the number of protons and neutrons inside the nucleus using a symbol of P and an N. So the number of protons equals the atomic number, if you don't know that yet. And the mass number is actually the number of protons plus the number of neutrons. So to fit N, you should do, it says here, or to find N, you need to do what? Okay? So let's go back and look at this one more time. Let me reread it. Protons and neutrons are located in the nucleus. Yes, they are. Write the number of the protons and neutrons inside the nucleus using the symbols of the P and the N when you're doing the Bohr model. Okay? So let's go ahead and just do that part. Let's say we're going to do a Bohr model for oxygen. Go to your periodic table, and I just so happen to have this one right here, oxygen. Oxygen has the atomic number of 8. Okay, so I'm just going to put right here atomic number of 8. And it has a mass number, what's it say on the paper? 15.999. Okay, so it says write the protons with the P and neutrons with the N, and also go ahead and give the number it has. So here's what it should look like. We've got an oxygen atom, and the atomic number, which so happens to be 8, equals the number of protons. Okay, so if it's 8, then I'm going to put 8 P, the little plus sign. But if I need to find the neutron number, what should I do? Well, the mass number is the proton number plus the neutron number. So what I do here, in this case then, is that we're going to get that mass number and we're going to subtract it, okay? And that's how we figure that out. So let me write that right here. So mass number subtract the atomic number equals the number of neutrons. All right? Because if the atomic number is the proton number only and the mass number is combining them, well, let's subtract that so that way we find out how, get out those proton, and then we can find out the amount of neutrons. Now, let's look at this mass number though. This mass number over here is 15.999. When it comes to this, every single mass on the periodic table is going to have some type of decimal points, and we'll talk about that soon too. But we round. We either leave that number as is or we're going to round up. We do not change the number down. So either this number is going to stay at 15 or it's going to go up to 16. Because it's 15.999, we're going to round this up to 16. And we are going to say, and I'm going to do this down here, 16 take away 8 equals 8. So inside the nucleus, we have 8 neutrons. This is in the nucleus. This is how you draw a Bohr model. Let's keep going back to the directions. The next part of our direction says here, though, that the electrons are located in the outside in orbitals, is what Bohr said. Atoms are electrically neutral. Remember, we highlighted and we starred that on that other page. So the number of electrons should equal what? If it's supposed to be neutral, it should equal the protons, the number of protons. Makes sense? If I got 8 protons, I should have 8 electrons. They should cancel each other out. If I have 22 protons, I better have 22 electrons. And they should cancel each other out. So it says I have 8 protons here. So I'm going to make sure that I'm going to say I have 8 electrons. And here's what Bohr said. The first orbital can contain and hold 2 electrons. So let's go ahead and do the first orbital. 1 electron, 2 electrons. I'm supposed to have 8. So 8 take away 2 equals 6 left over. Let's keep going. The second orbital contains up to 8. It can contain less, but no more than 8. And I have 6. The next thing that we should know as well is that we always fill the lower orbitals first, which are closer to the nucleus, must be full before you start to the next higher orbitals. Okay, so number 1, or orbital number 1, needs to be filled with 2 electrons first. Then you can go to the second orbital with 8. If you have extra electrons, you go to the third one. If you have extra, you continue to move and you move and you move. So we said that oxygen 16, why do they call it 16? They rounded the 15.999 up. Has 8 protons, 8 neutrons, and 8 electrons. Why? Because it's electrically neutral. So if I have 8 and I took away 2 for the first orbital, I have 6 left over. 1, 2, 3, 4, 5, 6. Okay? And I used up all 6. Done. Now let's go to this other word over here. Valence electrons. I'm sure you probably heard that word before as well. The word valence electron is the outer electrons. And they're going to be on the outer electrons on the last shell. So when we go back over here and we ask, or the questions ask, how many valence electrons are located in an oxygen atom? 6 valence electrons are located in this oxygen atom, because this is the last shell and we have 1, 2, 3, 4, 5, 6 electrons. Okay. Next thing though is that most atoms actually need 8 valence electrons to have a full shell. So draw a Bohr model for sodium atom with 11 protons, 12 neutrons, and 11 electrons. So they want us to go ahead and practice another one. Okay? Let's do that. I'm going to do that over here. How many protons do I have? I have 11 protons. How many neutrons? They told me 12 neutrons. That is located inside the nucleus. Then I have, it says here, 11 electrons. The first shell or orbit can only contain 1, 2. So 11 take away 2, 9. But the next one can only have 8 in it. So let's draw the next one. 1, 2, 3, 4, 5, 6, 7, 8. I have 9, take away 8, 1 left over. So I'm going to go ahead and draw my next one, 1. This question here says, how many valence electrons are located in this sodium? It has 1 valence electron. Okay, but let me show you the shortcut abbreviation for 1 valence electron. When we use the word electron and we're just talking about electron, it's an E. But when we're talking about valence electrons, it is 1 valence electron, VE. Okay? Practice again. Draw a Bohr model of a sulfur atom with 16 protons, 16 neutrons, and 16 electrons. Okay, let's do that. Protons are 16 protons, 16 neutrons. They're in the nucleus. And then on the outside, first shell can only contain 2. 1, 2. Second shell can have 8. So 16 take away 2 equals 14. 1, 2, 3, 4, 5, 6, 7, 8. So 14 take away 8 equals what? 6 left over? Let's keep going. 1, 2, 3, 4, 5, 6. Now I used them all up. How many valence electrons are in this sulfur atom? 6 valence electrons. Can you tell which of these Bohr models are incorrect? If they are incorrect, well then why are they incorrect? Let's look at letter A. Letter A, the first one has 2. Next one has 2, 4, 6, 8. 2, 4, 6, 8, and 1 left over. That looks great. Let's look at the next one. B. The first shell, which is right here, only has 1 electron. So this one definitely is incorrect. Why? Because the first shell has only 1 electron. That's why it's incorrect. Let's keep going. Letter C. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. Next shell. 1, 2, 3, 4, 5, 6, 7, 8. The next shell. 1, 2, 3. That's good. Letter D. 1, 2. Good. Let's go to the next shell. 1, 2, 3, 4, 5, 6, 7, 8. Good. 1, 2. That's good as well. Looks like letter B is the only one that's incorrect. Let's keep going. Now, that was the Bohr model. Since then, someone else came up with a better suggestion on how we should draw it out, and we call that the Lewis dot diagram. We like the Lewis dot diagram. It says here that the Lewis dot diagram is an arrangement of valence electrons around the element symbol. This symbol is going to be those letters. And how do you know you're only talking about one atom or one element? Because it has a capital letter always, and if there is a second letter, it's always lowercase. Okay? And for an example, CO2, that is a capital C, a capital O. Okay? If I want to combine lithium fluoride, lithium fluoride. Capital letter, lowercase, because there's 2 letters, but this is another capital, so I know I have 2 different elements. Okay? So around the symbol, it says here, place 1 electron around the 4 sides of the element symbol before pairing the electrons up with another one. So you're going to go 1, 2, 3, 4, 1, 2, 3, 4. Why? Because it says over here that pretty much most electrons like to have 8 in their outer shell, if I can find that. I know we just said that somewheres. I know it should be over here. That we know. Let's see. Most electrons like to have 8 so that way they can be full. Man, I know we saw it somewhere just recently, just a minute ago. And look at that, I can't even find it already. I'll probably find it whenever we have class, right? Snap. Let's see. That we know, but I know we saw it. I just went blank on where it's at though now. Maybe it's on the, it can't be on this previous page, is it? No. Let's see, on here. Let's see, over here. Over here. I don't think that's not there either. Well, my goodness. I cannot believe this. I lost it. We just talked about that. All right, so most atoms like to, and I say the word most, and I mean most of them. There's a couple that are a little different that are out there. But other than that, most atoms like to have, oh, here it is. Most atoms need 8 valence electrons to have a full valence shell. There's only a couple exceptions to the rule. And this is chemistry. We have exceptions to every single unit, believe it or not. So it says here now, since most atoms need 8 valence electrons to be full, the Lewis dot represents how many of the valence electrons are needed to make a full valence shell. Okay, so let's go ahead and practice this. For an example, we are looking at the valence electrons. Draw a Lewis dot structure for the following elements from the Bohr model over here. So, Bohr model A. We just did Bohr model A. What was Bohr model A? Bohr model A was this one, oxygen. Okay? And how many what was that? Bohr model A. Oh, sorry. Bohr model A. How many valence electrons does this one have? 1. So, Bohr model A has 1 valence electron. Okay? So, draw the Lewis dot structure for the following elements, which are over here, and from the Bohr models from above. Bohr model C. Let's come back over here. It was on the previous page. Bohr model, there it is, C. How many valence electrons? 1, 2, 3. So Bohr model C has 1, 2, 3. Bohr model D. Let's look at element D. 1, 2. 1, 2. We always start at the top of the element and work our way around from the right side and all the way around that way. We go in the direction from right all the way around. So let's go ahead and practice over here. Oxygen. We just did oxygen, right? And how many valence electrons were in oxygen? If you don't remember, let's go back to the previous page. How many? 6. Okay, start at the top. 1. Move to the right. 2, 3, 4, 5, 6. Sodium. Sodium is over here in A. It has 11 as the atomic number, which is the number of protons, which is also the number of electrons. So I'm going to come over here. First shell could only contain 2. We have 11. Take away 2 equals 9. All right. How many can the second shell contain? Up to 8. Take away 8. How many's left over? 1. That 1 is going to be the valence electrons. Sulfur. This is how we do the Bohr models. We come over here, we find sulfur, which is a nonmetal. Its atomic number is 16. Okay, so come over here and I'm going to write 16. The first shell can only contain 2. 14 are left over. All right, second shell can contain 8. Take away 8. 8, 9, 10. So that means 4, 5, 6 are left over. How many valence electrons? 6. Start always at the top. 1, 2, 3, 4, 5, 6. And that's how you draw the Bohr model. Which elements here above have the same number of valence electrons? Well, let's go ahead and see. This one has 6. 1, 2, 4, 5, 6. Okay. That has 1, that has 3, and that has 2. So oxygen and sulfur, and what else? Na, sodium, and element A. I'll put a line. So those two have the same, and those two have the same. If two elements have the same number of valence electrons, what does this mean? Okay, and I'm sure you talked about this previous than coming over here to collegiate. You've had a little bit of chemistry, and for an example, group 1, groups are the up and down columns. Every single person in group 1 has only 1 valence electron. Every single person in group 2 has 2 valence electrons. Every single person in group 3 has 3 valence electrons. So what does that mean? That means that they are from the same group. And I'm going to put right here in parentheses the columns, which are up and down. Okay? We're going to go ahead and pause there. We are definitely going to start from the beginning in class with our notes. And I will record the rest of this later on. Thank you.